You are inside a spacecraft. The engines are roaring with unimaginable power. The speedometer on your dashboard reads 297,000 kilometers per second. That is 99% the speed of light. At this speed, you could circle the entire Earth more than 7 times in a single second. You could travel from New York to London in less than the blink of an eye. You are moving faster than any human being has ever moved in the entire history of our species. You are moving faster than anything humans have ever built, ever designed, ever dreamed of building. You feel like a god of velocity. You feel like you have conquered the universe itself. But here is the thing that will shatter that feeling completely. At this extraordinary speed, reaching the nearest star to our Sun, a star called Proxima Centauri, would still take you more than 4 years. 4 years of traveling at 297,000 kilometers every single second. And Proxima Centauri is our neighbor. It is the closest star outside our solar system. The galaxy we live in, the Milky Way, contains somewhere between 100 billion and 400 billion stars. Most of them are thousands, tens of thousands, even hundreds of thousands of light years away from us. And beyond our galaxy, there are 2 trillion more galaxies in the observable universe. At 99% light speed, reaching even the nearest large galaxy, Andromeda, would take you more than 2.5 million years. Let that sink in. 2.5 million years. At 99% the speed of light. That is longer than our species has existed. Homo sapiens emerged roughly 300,000 years ago. So even if we had started this journey when our species first appeared on Earth, we would not even be close to arriving at Andromeda. We would have spent our entire evolutionary history inside that spacecraft and still have more than 2 million years of travel remaining. And here is where it gets even more disturbing. The observable universe is 93 billion light-years across, even at 100% the speed of light, which is physically impossible for anything with mass. Crossing the observable universe would take longer than the current age of the universe itself. And the universe is expanding. The distant galaxies are moving away from us. And not just moving away, but accelerating away. Some of them are already receding faster than the speed of light. Not because they are moving through space faster than light, but because space itself is stretching between us and them at a rate that exceeds light speed. This means there are galaxies we can see right now, whose ancient light reached us billions of years ago, that we can never, ever reach. Even if we traveled at the speed of light forever. They are beyond our cosmic horizon. They are gone. And every second, more galaxies cross that horizon and vanish from our potential reach permanently. So here is the question that this entire discussion will explore in depth. Why is 99% the speed of light not fast enough? What is it about the universe that makes this speed, this staggering, incomprehensible speed, inadequate for exploring even a tiny fraction of what exists? What happens to matter, to energy, to time itself, as you approach this cosmic speed limit? And most importantly, is there any way around it? Is there any loophole in the laws of physics that might someday allow us to truly explore the cosmos? We are going to cover everything. The physics of why light speed is the limit. What happens to your body, your clock, your mass as you get closer to that limit? The insane energy requirements. The problem of cosmic distances combined with the expanding universe. The engineering nightmares. And then we are going to explore the theoretical possibilities. Warp drives, wormholes, quantum physics, and what they might or might not offer. Every single claim will be backed by real research, real names, real dates, real numbers. No speculation presented as fact. No bias, just pure physics, deeply explored from every angle. If you are someone who loves understanding the universe at its deepest level, if you love having your intuition completely shattered by reality, then stay with me for this entire journey. Hit that subscribe button, because what we are about to explore will fundamentally change how you see the cosmos, how you see speed, and how you see humanity's place in this vast, beautiful, terrifying universe. Drop a comment right now with your guess. How fast do you think we actually need to go to explore the universe? I want to see what you think before we dive into what the physics actually says. Now let me start with a real story. A real event that perfectly illustrates why this topic matters so much. On April 12, 2016, something remarkable happened. A Russian-Israeli billionaire named Yuri Milner stood alongside one of the greatest physicists in human history, Stephen Hawking, and announced a project called Breakthrough Starshot. This was not science fiction. This was a real, funded, serious scientific initiative backed by $100 million. The goal was extraordinary. They wanted to send a spacecraft to Alpha Centauri, the nearest star system to our Sun, at about 4.37 light-years away. But here is what made it so striking. Their target speed was 20% the speed of light. Not 50%, not 99%, 20%. And even at that speed, the journey would take approximately 20 years. Think about what that means. Some of the smartest people on the planet, with $100 million, with access to the most advanced technology humanity has ever produced. Their ambitious goal was 20% the speed of light, and their spacecraft was not a ship carrying humans. It was a tiny chip. A gram-scale device called a star chip, thinner than a sheet of paper, pushed by a ground-based laser array with a power output of 100 gigawatts. That is equivalent to the total output of all the nuclear power plants on Earth focused into a single beam of light, pushing a chip that weighs less than a paperclip. All of this technology, all of this money, all of this genius for 20% of light speed, for a tiny chip, for a 20-year journey to the nearest star. Now ask yourself this. If the brightest minds on Earth are celebrating the mere possibility of reaching 20% light speed for a gram-scale chip, what does that tell you about reaching 99% the speed of light for a spacecraft carrying humans? And even if we could achieve that miracle, we have already established that 99% is not enough for any meaningful exploration of the universe beyond our immediate stellar neighborhood. This is the problem. This is the wall. And to truly understand why this wall exists, we need to go back in time. We need to go to a patent office in Bern, Switzerland, in the year 1905, where a 26-year-old clerk named Albert Einstein was about to destroy everything humanity thought it understood about space, time, speed, and the nature of reality itself. Before Einstein, people thought about speed the way you think about it in everyday life. If you are on a train moving at 100 kilometers per hour, and you throw a ball forward at 50 kilometers per hour relative to the train, then someone standing on the ground would see that ball moving at 150 kilometers per hour. Speeds add up. This seems so obvious that nobody questioned it for thousands of years. It is called Galilean relativity, and it works perfectly well for the speeds we encounter in daily life. But there was a problem. In 1865, a Scottish physicist named James Clerk Maxwell unified electricity and magnetism into a single theory. His equations predicted that electromagnetic waves, which include light, travel at a specific speed. That speed was approximately 299,792 kilometers per second. Maxwell's equations did not say relative to what. They just said light travels at this speed. Period. This was strange. Every other speed in physics is relative to something. The speed of a car is relative to the ground. The speed of a ball is relative to the person who threw it. But light seemed to have an absolute speed that did not depend on the motion of the source or the observer. This led to one of the most important experiments in the history of physics. In 1887, two American physicists named Albert Michelson and Edward Morley tried to detect the motion of the Earth through the hypothetical luminiferous ether, a medium that was supposed to carry light waves the way air carries sound waves. Their logic was simple. If the Earth is moving through the ether, then light traveling in the direction of Earth's motion should appear to move slightly slower relative to us, and light traveling perpendicular to Earth's motion should appear to move at its normal speed. The difference would be tiny, but their instrument, the Michelson interferometer, was sensitive enough to detect it. The result shocked the physics community. There was no difference. Zero. Light moved at exactly the same speed in every direction, regardless of the Earth's motion through space. This seemed impossible. It was as if you were running forward and shined a flashlight, and the light moved away from you at the same speed whether you were standing still or running at full sprint. That violates everything about how speeds should add up. For nearly 2 decades, physicists struggled with this paradox. And then came Einstein. As a teenager, Einstein had asked himself a deceptively simple question. What would happen if I could ride alongside a beam of light? If I were traveling at the speed of light, would the light beam appear stationary to me? According to classical physics, yes, but according to Maxwell's equations, a stationary electromagnetic wave makes no sense. The equations do not permit it. Something had to give. In June of 1905, Einstein published his paper on the electrodynamics of moving bodies in the journal Annalen der Physik. This paper contained what we now call special relativity, and it began with 2 simple postulates. First, the laws of physics are the same in all inertial reference frames. Second, the speed of light in vacuum is the same for all observers, regardless of the motion of the light source or the observer. From these 2 seemingly simple statements, Einstein derived consequences that shattered human intuition about the nature of reality. The speed of light is not just a speed, it is a fundamental constant of nature, woven into the very fabric of space-time. The number 299,792,458 meters per second is so fundamental that since 1983, the meter itself is defined in terms of it. 1 meter is officially defined as the distance light travels in 1/299,792,458 seconds. We do not measure the speed of light against the meter. We define the meter using the speed of light. That is how fundamental this constant is. But why? Why is there a speed limit at all? The answer lies deeper than just light. Light happens to travel at this speed because it is massless. But the speed itself is not really about light. It is about causality. It is about the maximum speed at which any information, any influence, any cause can propagate through the universe. Physicists sometimes call it the speed of causality rather than the speed of light, because that better captures what it truly is. It is the speed at which the fabric of space-time allows one event to influence another. Think of it this way. Space-time is not just a stage on which physics happens. Space-time is physics. It has properties. One of those properties is that it has a maximum speed of information transfer. This speed emerges from the geometry of space-time itself. In the mathematical language of relativity, space-time has a metric, a way of measuring distances between events. That metric has a built-in structure called the light cone, which divides all of space-time into regions that can and cannot influence each other. The light cone is defined by the speed of light. Nothing with mass can ever reach the boundary of the light cone. Nothing at all can go beyond it. Here is another way to think about it. In our everyday experience, we think of space and time as separate things. Space is where things are. Time is when things happen. Einstein showed that they are not separate. They are one unified thing called space-time, and they are connected through the speed of light. The speed of light is essentially the exchange rate between space and time. 1 second of time is equivalent to 299,792 kilometers of space. That is the conversion factor. And this conversion factor sets the absolute maximum speed. Everything in the universe is always moving through space-time at the speed of light. Yes, you, sitting still right now, are moving through space-time at the speed of light. The difference is the direction. When you are sitting still in space, all of your motion through space-time is directed through time. You are moving through time at the maximum rate. When you start moving through space, you are redirecting some of your space-time motion from the time direction to the space direction. The faster you move through space, the slower you move through time. And if you could move through space at the speed of light, all of your space-time motion would be in the space direction. And you would move through time at 0 rate. Time would stop for you. But this is impossible for anything with mass because it would require infinite energy. Now let us explore what actually happens as you approach this speed limit, because the consequences are among the strangest phenomena in all of physics. The first, and perhaps most famous consequence, is time dilation. As your speed increases toward the speed of light, time for you literally slows down relative to someone who is not moving. This is not a trick, it is not an illusion, it is not about clocks malfunctioning. Time itself, the actual progression of physical processes, runs slower for you. Your heart beats slower, your thoughts form slower, your biological aging slows. Everything. The mathematical formula for this is elegant and precise. The time dilation factor, called gamma or the Lorentz factor, equals 1 divided by the square root of 1 minus v squared over c squared, where v is your velocity and c is the speed of light. At low speeds, this factor is essentially 1, meaning there is no noticeable effect. At 50% the speed of light, gamma equals about 1.15, meaning your time runs about 15% slower. But as you approach the speed of light, this factor shoots up dramatically. At 90% the speed of light, gamma is approximately 2.3. Time passes for you at less than half the rate it passes for someone on Earth. At 99% the speed of light, gamma is approximately 7.09. For every 7 years that pass on Earth, you experience only 1 year. At 99.9% the speed of light, gamma jumps to approximately 22.4. For every 22 years on Earth, you experience 1. At 99.99%, gamma is about 70.7, and at 99.9999% the speed of light. Gamma reaches approximately 707. For every 707 years that pass on Earth, you experience only 1 year. This is not science fiction. This has been experimentally confirmed multiple times with extraordinary precision. In 1971, physicists Joseph Hafele and Richard Keating placed extremely precise atomic clocks on commercial aircraft that flew around the world, eastward and westward. When they compared these clocks to identical clocks that remained on the ground, the clocks on the aircraft had ticked differently. The eastbound clocks lost 59 nanoseconds. The westbound clocks gained 273 nanoseconds. These numbers matched Einstein's predictions to within experimental uncertainty. Time dilation is real. Even more dramatically, every single GPS satellite orbiting Earth carries atomic clocks that must be corrected for time dilation. These satellites move at about 14,000 kilometers per hour, which is incredibly slow compared to light, but still fast enough for relativistic effects to matter when you need GPS accuracy. Without corrections for both special relativistic time dilation and general relativistic effects from gravity, the GPS system would accumulate errors of about 10 kilometers per day. Every time you use GPS on your phone, you are relying on Einstein's relativity working correctly. Particle accelerators provide even more dramatic confirmation. Muons are subatomic particles created when cosmic rays hit the upper atmosphere. They have a half-life of about 2.2 microseconds. At the speed they travel, about 99.95% the speed of light. They should only be able to travel about 660 meters before decaying, but we detect them at the surface of the Earth after traveling many kilometers through the atmosphere. How? Time dilation. In the muon's frame of reference, its lifetime is unchanged, but from our perspective, its time is running so slowly that it survives long enough to reach the ground. This has been measured thousands of times. It works every single time. Now here is what time dilation means for interstellar travel. At 99% the speed of light, a journey to Alpha Centauri at 4.37 light-years distance would take about 4.4 years in Earth time. But for the traveler, due to time dilation with a gamma of about 7, the journey would feel like only about 7.5 months. That sounds amazing. But here is the catch. When you arrive at Alpha Centauri and send a message back to Earth, more than 4 years have already passed on Earth since you left. If you turn around and come back at the same speed, you return to an Earth where more than 8 years have passed, while you have aged only about 15 months. This is the famous twin paradox, though it is not actually a paradox at all. It is simply the confirmed physics of special relativity. One twin stays home. The other twin travels at high speed to a distant star and returns. When they reunite, the traveling twin is genuinely younger. Their body has aged less. Their cells have divided fewer times. They have experienced less time in every measurable way. This is real. It is not a matter of perception or measurement error. The traveling twin truly, physically lived through less time. But notice something critical. While time dilation helps the traveler, it does nothing for the people left behind. If you travel to a star 1,000 light-years away at 99% the speed of light, you might experience only about 140 years of subjective time due to time dilation. But back on Earth, more than 1,010 years have passed. Everyone you knew is dead. Their children are dead. Their civilizations may have risen and fallen. For the traveler, time dilation is a gift. For everyone else, it is irrelevant. The second major consequence of approaching light speed is length contraction. As you move faster, distances in your direction of travel literally shrink. This is not an optical illusion. Space itself, in your frame of reference, contracts at 99% the speed of light with a gamma of about 7, the 4.37 light-year distance to Alpha Centauri contracts to about 0.62 light-years in your frame. That is why the journey feels shorter to you. Not just because your clock is slow, but because the distance is literally shorter in your reference frame. Again, this is confirmed experimentally. Those muons I mentioned earlier, from their perspective, they are not living longer. They are living their normal 2.2 microseconds. But the distance from the upper atmosphere to the ground is contracted in their frame of reference. The 10 kilometers or so of atmosphere appears much shorter to them, so they can traverse it in their normal lifetime. But here is the key insight that many people miss. Length contraction only occurs in the direction of motion, and it only helps you, the traveler. The actual distance, as measured by anyone not on your ship, remains unchanged. The universe did not get smaller. Your experience of crossing it changed, and the moment you slow down or stop, the full distance reasserts itself in your frame. The third, and perhaps most devastating consequence for space travel, is what happens to your mass, or more precisely, to your inertia and the energy required to accelerate you further. As your speed increases toward the speed of light, the energy required to accelerate you grows without bound. The total energy of a moving object is gamma times m times c squared. At 99% the speed of light, your total energy is about 7 times your rest mass energy. That means your effective resistance to further acceleration, your inertia, has increased 7-fold. Let me put this in concrete terms. Consider a spacecraft with a mass of 100,000 kilograms, about the mass of a large aeroplane. To accelerate this spacecraft to 99% the speed of light would require an amount of energy approximately equal to 5.3 times 10 to the 21st joules. That is 5.3 sextillion joules. For comparison, the entire world's energy consumption in a year is approximately 5.8 times 10 to the 20 joules. So accelerating a single airplane mass spacecraft to 99% light speed would require roughly 90 times the total annual energy consumption of all human civilization. For one ship, for one trip, without considering the energy needed to slow down at the destination. And it gets worse the faster you go. Going from 99% to 99.9% light speed does not cost just a little more energy. It costs enormously more. The energy curve is not linear. It is not even simply exponential. It is asymptotic. It shoots toward infinity as you approach the speed of light. Going from 99.9% to 99.99% costs even more proportionally. Each additional 9 after the decimal point costs dramatically more energy than the last, and reaching 100%, exactly the speed of light, would require literally infinite energy. This is not an engineering problem. It is not about having better engines or more fuel. It is a fundamental mathematical property of spacetime. The asymptotic nature of the Lorentz factor means that no finite amount of energy can ever accelerate any object with mass to exactly the speed of light. The universe has built an impenetrable wall at velocity c, and no technology, no matter how advanced, can breach it if it respects the known laws of physics. Let me drive this point home with a specific comparison. The most powerful nuclear weapon ever detonated was the Soviet Tsar bomber in 1961, which released about 210 million billion joules of energy. To accelerate just 1 kilogram of matter to 99% the speed of light requires about 5.3 times 10 to the 16 joules, equivalent to roughly 12.7 megatons of TNT, or about 850 Hiroshima bombs worth of energy. For 1 kilogram. A single kilogram. A bag of flour. Now imagine accelerating a crude spacecraft. Even a small one, say 10,000 kilograms. You would need the energy equivalent of millions of nuclear weapons. And then you need roughly the same amount of energy again to slow down. And you need to carry all that energy with you, which adds mass, which requires more energy to accelerate, which adds more mass, which requires more energy. This is the tyranny of the rocket equation, and at relativistic speeds, it becomes absolutely crushing. The rocket equation, derived by Konstantin Tsiolkovsky in 1897, states that the change in velocity of a rocket equals the exhaust velocity times the natural logarithm of the initial mass divided by the final mass. For conventional chemical rockets, the exhaust velocity is about 4.5 kilometers per second. To reach even 10% the speed of light with a chemical rocket, you would need a mass ratio so enormous that it exceeds the mass of the observable universe. That is not an exaggeration. The math literally gives you a number larger than the mass of everything we can see. Even with the most efficient propulsion theoretically possible, matter-antimatter annihilation, the mass ratio for reaching 99% the speed of light is staggering. In matter-antimatter annihilation, 100% of the mass is converted to energy via E equals mc squared. This is the most efficient energy source permitted by physics. Nothing can be better. Yet even with perfect antimatter propulsion, reaching 99% the speed of light and then decelerating at the destination requires a mass ratio of roughly 40:1. For every kilogram of payload that arrives, you need 40 kilograms at the start. Almost all of it antimatter fuel. For a minimal crewed spacecraft of say 10,000 kilograms, you would need 400,000 kilograms of antimatter. Let me put that in perspective. The total amount of antimatter produced by all the particle accelerators in human history, including CERN's Large Hadron Collider, amounts to approximately 10 to 20 nanograms. A nanogram is 1/billionth of a gram. We have produced roughly 10 billionths of a gram of antimatter in our entire history. We need 400 million grams. The gap between what we have and what we need is roughly 20 quintillion-fold. And the cost of producing antimatter with current technology is estimated at about $62.5 trillion per gram. The total economic output of all human civilization throughout all of history would not buy enough antimatter to fuel a single interstellar trip at 99% light speed. But even if we somehow solved the energy problem, even if we had unlimited free energy and unlimited antimatter, the problems do not end. Let us talk about what happens when you actually try to move through space at 99% the speed of light. Space is not empty. This is one of the most important facts that science fiction consistently ignores. The interstellar medium, the space between stars, contains roughly 1 to 2 hydrogen atoms per cubic centimeter. That sounds like almost nothing, and at normal speeds, it effectively is nothing. But at 99% the speed of light, everything changes. When your spacecraft moves through these sparse hydrogen atoms at 99% the speed of light, each atom hits your ship with enormous kinetic energy. From your ship's frame of reference, these atoms are screaming toward you at 99% the speed of light. The kinetic energy of each hydrogen atom at this speed is given by the relativistic formula, and it works out to approximately 6 times the energy of the most energetic cosmic rays ever detected. At this speed, the interstellar hydrogen is not hitting you like a gentle breeze. It is hitting you like a continuous stream of high-energy radiation. The flux of hydrogen atoms at interstellar densities and 99% light speed creates a radiation environment equivalent to standing directly next to an unshielded nuclear reactor core. The radiation dose would be lethal to any biological organism within minutes. And it is not just hydrogen. The interstellar medium also contains dust grains. These are tiny particles, typically a fraction of a micrometer in size, composed of silicates, carbon, or ice. At rest, they are completely harmless. At 99% the speed of light, a single dust grain carries the kinetic energy of several kilograms of TNT. A slightly larger grain, say the size of a sand particle, would carry the energy of a tactical nuclear weapon. Your spacecraft would be subject to continuous bombardment by what effectively amounts to nuclear-scale impacts from microscopic particles. Any shielding you add to protect against this bombardment adds mass to your spacecraft. More mass means you need more energy to accelerate. More energy means more fuel. More fuel means more mass. The feedback loop makes the entire proposition exponentially harder. There is also the problem of radiation from the cosmic microwave background. At rest, the cosmic microwave background is a gentle bath of microwave radiation at about 2.7 Kelvin, completely harmless. But when you move at 99% the speed of light, the cosmic microwave background in front of you is blue-shifted, dramatically blue-shifted. Radiation that was harmless microwave radiation gets shifted up in frequency, through infrared, through visible light, through ultraviolet, all the way into the X-ray range. Your spacecraft is being irradiated by what appears to be an intense X-ray source directly ahead of you, simply because you are moving so fast through the universe's background radiation. And then there is navigation. At 99% the speed of light, the universe looks completely different. A phenomenon called relativistic aberration causes the apparent positions of stars to shift forward. Stars that were to your sides appear to crowd toward the front of your view. Stars behind you appear to shift further back or disappear entirely. The visible universe appears to compress into a bright spot ahead of you and a dark void behind. Furthermore, stars ahead of you are blue-shifted to higher frequencies, while stars behind are red-shifted to lower frequencies. Your view of the universe becomes increasingly distorted and unfamiliar the faster you go. Communication with Earth becomes extraordinarily difficult. If you send a radio message back while traveling at 99% light speed, the message is dramatically redshifted, and as you get further from Earth, the time delay grows. Any meaningful two-way communication becomes impossible once you are more than a few light years away. You are essentially on your own. Let us also consider the human body itself. Acceleration is a critical factor. You cannot simply jump to 99% light speed instantaneously. The human body can withstand about 3 to 5 g of sustained acceleration. At 1 g of constant acceleration, which would feel like normal Earth gravity inside the ship, reaching 99% the speed of light takes approximately 2.3 years. At 3 g, it takes about 9 months. The acceleration itself is survivable, but during that entire acceleration phase, you are consuming fuel at an enormous rate, and you need to save enough fuel for an equally long deceleration phase at the destination. Now we come to what I consider the most profound aspect of this entire discussion: the scale problem. Even if we magically solved every single engineering challenge I just described, even if we had infinite energy, perfect shielding, no radiation problems, and could comfortably cruise at 99% the speed of light, the distances of the universe are so staggeringly, incomprehensibly vast that 99% light speed is still nowhere near sufficient for any meaningful exploration. Let me walk you through the distances we are dealing with. Starting small and expanding outward. Proxima Centauri, the nearest star, is 4.24 light-years away. At 99% light speed, this takes about 4.28 years Earth time. That is actually reasonable. You could go there and come back within a decade. But now let us look further. The TRAPPIST-1 system, which contains 7 Earth-sized rocky planets, some in the habitable zone, is 39.6 light-years away. At 99% light speed, that is about 40 years Earth time. A human lifetime just for one trip, no return. The center of our own galaxy is 26,000 light-years away. At 99% light speed, that takes 26,262 years. Our species has not existed for that long. No human civilization has lasted even a fraction of that time. The nearest large galaxy, Andromeda, is 2.537 million light-years away. At 99% light speed, the journey takes 2.56 million years. Longer than our species has existed. Longer than the entire genus Homo has existed. And the edge of the observable universe is 46.5 billion light-years away. At 99% light speed, the journey would take 46.97 billion years. The universe itself is only 13.8 billion years old. You would need more than 3 times the current age of the universe to make this trip. These numbers should fill you with a kind of cosmic vertigo. The universe is not just big. It is big in a way that defeats even the most extraordinary speeds we can imagine. 99% light speed sounds incredible from a human perspective. But from the universe's perspective, it is almost nothing. It barely gets you to the nearest star. But wait, it gets worse. Much worse. Because the universe is not just sitting there, static, waiting for us to cross it. It is actively expanding. And not just expanding, but accelerating in its expansion. In 1929, American astronomer Edwin Hubble published observations showing that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it is receding. This was the first observational evidence that the universe is expanding. But at that time, most scientists assumed the expansion was slowing down due to the gravitational attraction of all the matter in the universe. Then in 1998, 2 independent teams of astronomers made a discovery that shocked the world and eventually won them the Nobel Prize in Physics in 2011. Saul Perlmutter led one team, and Brian Schmidt and Adam Rees led the other. By observing distant Type Ia supernovae, which serve as standard candles because their intrinsic brightness is known, they measured the expansion rate of the universe at different times in its history. What they found was stunning. The expansion of the universe is not slowing down, it is speeding up. Something is pushing the universe apart faster and faster over time. This accelerating expansion is attributed to what we call dark energy, which constitutes approximately 68% of the total energy content of the universe. We do not know what dark energy is. We do not understand its fundamental nature, but its effects are clearly measured. It is causing the expansion of the universe to accelerate. The rate of this expansion is described by the Hubble constant, which is approximately 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So this means that for every 3.26 million light-years of distance, space is expanding at an additional 70 kilometers per second. The further away something is, the faster it recedes. Here is the critical implication. At a certain distance, the expansion of space causes objects to recede from us at the speed of light. This distance defines what is called the Hubble sphere, and it is currently about 14.7 billion light-years away. Beyond this distance, objects are receding from us faster than the speed of light. They are not moving through space faster than light, which would violate relativity. Rather, the space between us and them is expanding faster than light can cross it. This distinction is crucial. Special relativity says nothing can move through space faster than light. But it places no restriction on how fast space itself can expand. This means that even at the speed of light, you could never reach objects beyond the Hubble sphere. They are receding too fast. And because the expansion is accelerating, the Hubble sphere is not growing fast enough to keep up. Objects are constantly crossing out of our potentially reachable universe. Let me explain this with a more precise concept. Cosmologists distinguish between the observable universe and the reachable universe. The observable universe has a radius of about 46.5 billion light-years. This is everything whose light has had time to reach us since the Big Bang. But the reachable universe, the region we could theoretically visit if we left right now at the speed of light and traveled forever, is much smaller. Current estimates put the reachable universe at roughly 18.3 billion light-years in radius, and this number is shrinking. Due to the accelerating expansion, the boundary of the reachable universe is contracting over time. Galaxies that we could reach today, we will not be able to reach tomorrow. This is the cosmic event horizon. Just like a black hole has an event horizon beyond which nothing can escape, the accelerating universe has a cosmological event horizon beyond which we can never travel. And galaxies are crossing this horizon all the time, disappearing from our potential reach forever. In approximately 100 billion years, due to the accelerating expansion, every galaxy outside our local group will have crossed beyond our cosmological event horizon. Observers at that time will look out into space and see only their local group. The rest of the universe will be invisible and unreachable. They will not even know it exists unless they have records from earlier eras. This is perhaps the most profound and disturbing implication of the accelerating expansion. The universe is not just too big for us to explore, it is actively erasing itself from our potential reach. The reachable universe is shrinking every single day. We are on a cosmic clock, and it is running out. Every moment we delay developing interstellar travel, more of the universe becomes permanently inaccessible. So let us now combine all of these factors. The speed of light is the absolute maximum speed for anything with mass, and we cannot even reach it. The energy required to approach it is astronomical beyond imagination. The engineering challenges of surviving interstellar space at high speed are immense. The distances between stars, between galaxies, between the structures of the universe are so vast that even light speed would take millions or billions of years to cross. And the universe is expanding, accelerating, actively pushing everything further apart and making more of itself unreachable. 99% the speed of light is not just a little bit too slow. It is fundamentally, categorically inadequate for any meaningful exploration of the universe beyond our immediate stellar neighborhood. The handful of stars within 10 or 20 light-years of us are potentially accessible at this speed, yes, but the broader galaxy, the galactic clusters, the cosmic web of structure, the billions of galaxies we can see in our telescopes, they are as far beyond our reach at 99% light speed as the moon was beyond the reach of ancient humans who could only walk. If this realization disturbs you, if it fills you with a sense of cosmic claustrophobia, then you are feeling exactly what you should feel. The universe is a prison of distance, and the speed of light is the lock on the cell door. But before we despair, let us ask the question that drives all of physics forward. Are there loopholes? Are there ways around this barrier that do not violate the known laws of physics? To explore this question, we need to enter the realm of quantum mechanics. Because at the smallest scales, the universe behaves in ways that seem to defy everything we have just discussed. And while quantum mechanics has not yet given us faster than light travel, it has revealed some extraordinary phenomena that suggest the story is more complex than special relativity alone would indicate. The most famous of these phenomena is quantum entanglement. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper that was meant to show that quantum mechanics was incomplete. They described a phenomenon where two particles, once they have interacted, become entangled in such a way that measuring a property of one particle instantly determines the corresponding property of the other, regardless of the distance between them. Einstein called this spooky action at a distance and argued it proved quantum mechanics was missing something. but experiments have consistently shown that entanglement is real. The definitive experiments began with physicist John Bell, who in 1964 published a theoretical paper showing that if quantum mechanics was correct and no hidden variables existed, then measurements on entangled particles would violate certain mathematical inequalities. In 1982, French physicist Alain Aspect performed an experiment that confirmed quantum mechanics and violated Bell's inequalities. The correlations between entangled particles are real, instantaneous, and work regardless of distance. So, does this mean information can travel faster than light through entanglement? No, absolutely not. And this is one of the most important and most misunderstood points in modern physics. Entanglement creates correlations between particles, but it cannot be used to send information. Here is why. When you measure an entangled particle, you get a random result. You cannot control what result you get. If you measure the spin of your entangled electron, you might get up or down with equal probability. The measurement on your partner's entangled electron will then give the opposite result when they measure in the same direction. But since your result was random and you could not choose it, you have sent no information to the other party. They also get a random result. It is only when you later compare your results through a normal, slower-than-light communication channel that you notice the correlations. This is proven mathematically by what is called the no communication theorem. It demonstrates rigorously that no measurement on one part of an entangled system can be used to transmit information to the holder of the other part. The correlations are real, but they are useless for signaling. Nature seems to have built faster-than-light correlations into reality and then made absolutely certain we cannot use them for communication. This is a pattern that appears again and again in physics. The universe seems to flirt with faster-than-light phenomena while always maintaining the light speed barrier for actual information transfer. It is as if the speed of light is not just a limit, but a deeply protected principle. Every apparent loophole, when examined carefully, turns out to preserve it. Another quantum phenomenon that appears to violate the speed limit is quantum tunneling. In quantum mechanics, particles do not have definite positions. They are described by probability waves. A particle approaching a barrier, like an electron approaching a gap it does not have enough energy to cross classically, has a probability wave that extends through the barrier. There is a non-zero probability of finding the particle on the other side of the barrier, even though classically it should not be able to get there. In 1962, physicist Thomas Hartmann predicted that the time it takes for a particle to tunnel through a barrier appears to be independent of the barrier's thickness. This is called the Hartmann effect, and experiments have confirmed it. If the tunneling time is constant regardless of barrier thickness, then for a sufficiently thick barrier, the particle would seem to traverse it at speeds greater than light. But careful analysis reveals that no usable information travels faster than light in tunneling either. The probability wave exists on both sides of the barrier from the start. What appears to be faster than light transit is actually a consequence of how we define arrival for a wave packet. The leading edge of the probability wave was always on the other side. No signal, no energy, and no information actually crosses the barrier faster than light. Once again, the speed limit is preserved. There is also the concept of tachyons, hypothetical particles that travel only faster than the speed of light. In the framework of special relativity, particles with real positive mass must always travel slower than light. Massless particles like photons must always travel exactly at light speed. But the equations also permit a third category: particles with imaginary rest mass that always travel faster than light and can never slow down to light speed. These are called tachyons. Tachyons, if they existed, would have bizarre properties. From our perspective, they would travel backward in time. They could arrive at their destination before they left their source. They would violate causality. And in quantum field theory, when a field has tachyonic behavior, what it actually indicates is not a real faster-than-light particle, but rather an instability in the vacuum. The field wants to settle into a lower energy state. The tachyon is a mathematical signal of instability, not a physical particle. Despite decades of searching, no experimental evidence for tachyons has ever been found. Every experiment designed to detect faster-than-light particles has returned null results. The consensus in physics is that tachyons do not exist as real particles, and that the speed of light barrier is absolute. Now let us turn to quantum field theory more broadly, because it provides perhaps the deepest understanding of why the speed of light is so fundamental. In quantum field theory, all particles are excitations of underlying quantum fields that pervade all of spacetime. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. These fields obey equations that build the speed of light directly into their structure. The fundamental requirement in quantum field theory is called Lorentz invariance. This means the equations of the fields must look the same to all observers regardless of their velocity. This requirement automatically enforces the speed of light as the maximum speed of propagation for any disturbance in any field. You cannot have a Lorentz invariant quantum field theory that permits faster-than-light signaling. The mathematics forbids it. This is why the speed of light limit is so robust. It is not just one law. It is embedded in the very framework of our most successful physical theories. Special relativity, general relativity, quantum mechanics, quantum field theory, the standard model of particle physics, all of them incorporate the speed of light as a fundamental constant and enforce it as a speed limit. To violate it, you would not just need to overturn one theory. You would need to overturn the entire foundation of modern physics. But there is one area where the speed of light limit becomes more nuanced, and that is general relativity. Einstein published general relativity in 1915, 10 years after special relativity. General relativity describes how mass and energy curve spacetime, and how this curvature is what we experience as gravity. And within general relativity, something remarkable happens. While nothing can move through space faster than light, space itself has no speed limit. We have already discussed this in the context of the expanding universe. Distant galaxies recede from us faster than light because space between us and them is expanding. This does not violate relativity because the galaxies are not moving through their local space faster than light. Space itself is carrying them away. This distinction is not just a technicality, it is a potential loophole. If space itself can expand faster than light, could we somehow manipulate space to move us faster than light? Could we create a bubble of warped spacetime that carries us along like a surfer on a wave, while we remain stationary within our bubble? This is exactly what Miguel Alcubierre proposed in 1994. Alcubierre was a Mexican theoretical physicist who published a paper titled The Warp Drive, Hyper-Fast Travel Within General Relativity in the journal Classical and Quantum Gravity. His idea was elegant and audacious. Imagine a region of flat, undistorted spacetime, like a calm pool. Your spacecraft sits in this region, experiencing no acceleration, no time dilation, nothing unusual. Now imagine that the space in front of this bubble is contracting, getting smaller, while the space behind the bubble is expanding, getting larger. The net effect is that the bubble, with your ship inside it, moves forward through space at an arbitrarily high velocity. The ship is not moving through space, space is moving the ship. Inside the bubble, the ship is perfectly stationary. No speed limit is violated because the ship's local velocity is zero. It is space-time itself that is being manipulated, and there is no speed limit on how fast space-time can warp or expand. Alcubierre showed that the mathematics of general relativity permit this configuration. The Einstein field equations have solutions that describe this kind of space-time geometry. A warp drive is consistent with general relativity. This was a stunning result. But there are enormous problems. The original Alcubierre metric required something called exotic matter, matter with negative energy density. This is matter that has less energy than empty space, which seems contradictory to everything we know about normal matter. The amount required in Alcubierre's original calculation was staggering, equivalent to the negative of the mass energy of the planet Jupiter. You would need to somehow acquire a Jupiter mass quantity of exotic matter and configure it precisely around your ship. In 2012, Harold White, a physicist at NASA's Johnson Space Center, published modifications to Alcubierre's design that he claimed could reduce the exotic matter requirement dramatically, potentially down to about 700 kilograms. His key insight was that changing the shape of the warp bubble from a flat ring to a more rounded configuration reduced the energy requirements by many orders of magnitude. White even set up a small experiment at NASA's Eagleworks laboratory, attempting to detect microscopic space-time warping using a modified Michelson interferometer. The results were inconclusive, and the experiment was highly controversial within the physics community. In 2021, physicist Eric Lentz at the University of Göttingen published a paper proposing what he called soliton solutions to the warp drive problem. These solutions described configurations of positive energy that could theoretically achieve faster than light travel without requiring exotic matter at all. If correct, this would remove the biggest theoretical obstacle to the Alcubierre drive. However, the energy requirements in Lentz's solutions, while using only positive energy, were still enormous, equivalent to many times the mass energy of the visible universe, and many physicists remain skeptical that the solutions actually represent physically realizable spacetimes. There are other fundamental problems with warp drives beyond just the energy requirements. In 2009, physicists Stefano Finazzi, Stefano Liberati, and Carlos Barcelo published an analysis showing that the inside of a warp bubble would be causally disconnected from the bubble wall. This means that once the warp bubble is moving at faster than light speeds, the pilot inside cannot send signals to the bubble wall to control it, speed it up, slow it down, or stop it. You would need to pre-program the entire journey before departure. Any course correction would be impossible during faster-than-light travel. Additionally, simulations have shown that a warp bubble decelerating from faster-than-light speeds would release enormous bursts of radiation in the forward direction. The blue-shifted particles that accumulate on the front of the bubble during travel would be released as a devastating pulse of high-energy radiation when the bubble slows down. Anything at your destination would be incinerated before you arrived. Despite these challenges, the Alcubierre drive remains an active area of theoretical research because it demonstrates something profound. The mathematics of general relativity does not absolutely forbid faster than light travel. It makes it extraordinarily difficult and potentially impractical, but not impossible in principle. This is qualitatively different from special relativity's absolute prohibition on faster-than-light motion through space. General relativity says you cannot move faster than light, but space itself might carry you faster if you can figure out how to manipulate it. Another potential solution from general relativity is wormholes. In 1935, the same year Einstein and his colleagues wrote about quantum entanglement, Einstein and physicist Nathan Rosen published a paper describing what are now called Einstein-Rosen bridges. These are theoretical connections between two distant points in spacetime. shortcuts through the geometry of the universe. Imagine taking a sheet of paper and drawing two dots far apart. The distance between them along the paper might be 30 centimeters. But if you fold the paper so the dots are right next to each other and poke a hole through, you can connect them with a path of essentially zero length. A wormhole is the space-time equivalent of this. 2 points that are billions of light years apart through normal space might be connected by a wormhole throat only meters long. The problem with Einstein-Rosen bridges is that they are unstable. They collapse faster than anything can traverse them. In 1988, physicists Kip Thorne and Michael Morris at Caltech published a paper exploring what conditions would be needed to hold a wormhole open long enough for travel. Their conclusion was the same exotic matter required for the Alcubierre drive, matter with negative energy density. Thorne and Morris showed that if you could line the throat of a wormhole with exotic matter, the negative energy density would counteract the natural tendency of the wormhole to collapse, keeping it open indefinitely and allowing traversal. The amount of exotic matter required depends on the size of the wormhole, but for a human traversable wormhole, it would be substantial. Can exotic matter exist? In the strict sense required by wormholes and warp drives, we do not know. But there is one known physical phenomenon that produces something resembling negative energy density: the Casimir effect. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged metallic plates, placed very close together in vacuum, would experience an attractive force. This force arises from quantum vacuum fluctuations. In quantum field theory, empty space is not truly empty. It seethes with virtual particles popping in and out of existence. Between the plates, some wavelengths of these fluctuations are excluded because they do not fit between the plates. Outside the plates, all wavelengths are present. This creates a pressure differential that pushes the plates together. Crucially, the energy density between the plates is lower than the energy density of normal empty space. In a sense, it is negative. Part 2. Relative to the vacuum. This was experimentally confirmed in 1997 by Steve Lamoureux at the University of Washington, who measured the Casimir force with remarkable precision and found it matched theoretical predictions. So nature does allow something resembling negative energy density. The problem is scale. The Casimir effect produces incredibly tiny amounts of negative energy over incredibly small distances. The energy is proportional to the inverse fourth power of the plate separation. To get meaningful amounts of negative energy, you would need plates separated by subatomic distances, and even then the total energy would be far too small for any macroscopic application like stabilizing a wormhole. There is another tantalizing theoretical connection between wormholes and quantum mechanics that deserves mention. In 2013, physicists Juan Maldacena and Leonard Susskind proposed what is known as the ER equals EPA conjecture. ER refers to Einstein-Rosen bridges, and EPA refers to Einstein-Podolsky-Rosen entanglement. Their conjecture states that every pair of entangled particles is connected by a microscopic wormhole. This is a profound claim. It suggests that quantum entanglement, the spooky action at a distance that Einstein was so uncomfortable with, is actually a manifestation of space-time geometry. Two entangled particles are literally connected through a tiny wormhole in space-time. If this conjecture is correct, it means that wormholes are not exotic hypothetical objects. They are everywhere, connecting every pair of entangled particles in the universe. But these are not traversable wormholes. They are Planck-scale quantum wormholes, far too small for anything macroscopic to pass through, and the no-communication theorem still prevents information from being sent through the entanglement. The ER equals EPA conjecture does not give us a way to build a usable wormhole, but it does suggest that the connection between quantum mechanics and space-time geometry is far deeper than we currently understand. And in that deeper understanding, there might be possibilities we cannot yet imagine. Let me also address the possibility of higher dimensions. String theory, which is our leading candidate for a theory of quantum gravity, requires the existence of extra-spatial dimensions beyond the three we perceive. In different versions of string theory, the total number of space-time dimensions is 10 or 11. The extra dimensions are believed to be compactified, curled up at incredibly tiny scales, roughly the Planck length of 10 to the minus 35 meters. Could these extra dimensions offer shortcuts through our familiar three-dimensional space? In principle, the answer is possibly yes. Just as a two-dimensional being confined to the surface of a sphere cannot take a straight-line shortcut through the sphere's interior, but a three-dimensional being could. We as three-dimensional beings might be able to shortcut through a higher dimensional space that we cannot directly perceive. In brain-world scenarios, which are a subset of string theory models, our observable universe is a three-dimensional brain floating in a higher dimensional bulk. If other brains exist in the bulk, parallel universes essentially, the distance between them through the bulk might be very small, even if the distance along our brain is enormous. This is highly speculative, and there is currently no experimental evidence for extra dimensions or brain worlds. Some physicists have explored the idea that gravity, which in string theory can propagate through all dimensions including the bulk, might someday offer evidence for extra dimensions. If extra dimensions exist, gravitational experiments at very small scales might detect deviations from Newton's inverse square law. Experiments searching for this have so far found nothing, placing constraints on the size and number of extra dimensions. Let me now talk about another approach to the light speed problem that does not attempt to break the limit, but instead tries to work within it. This approach acknowledges that faster-than-light travel may be physically impossible, and asks, given this constraint, how can we still explore the cosmos? One answer is the generation ship concept. Instead of traveling fast, you travel slow and plan for the journey to take generations. A generation ship would be a massive, self-sustaining spacecraft designed to support a population of thousands of people for centuries or millennia. People would be born, live their lives, and die on the ship. Their descendants, many generations later, would eventually arrive at the destination. At 1% the speed of light, about 3,000 kilometers per second, which is still far beyond our current capabilities, but perhaps achievable with advanced fusion or antimatter propulsion, the journey to Alpha Centauri would take about 430 years. That is roughly 15 to 20 human generations. Not unimaginable. Civilizations on Earth have lasted longer than that. The Roman Empire, in various forms, lasted about 1,500 years. But the challenges of a generation ship are immense. You need a closed ecological system that can sustain itself for centuries without resupply. Every molecule of air, water, and food must be recycled perfectly. Any small imbalance that accumulates over centuries could be catastrophic. You need genetic diversity sufficient to avoid inbreeding over many generations, which means a minimum population of several thousand at least. You need social and political systems stable enough to maintain the ship's mission over time, spans much longer than any Earth civilization has remained stable. There are also psychological challenges. The people who launch the ship choose the mission. Their children do not. Their grandchildren do not. At what point does the crew begin to question why they are on this ship? Why should Generation 15 sacrifice for a destination they will never see, chosen by ancestors they never knew? The social engineering required for a multi-generational mission may be harder than the physical engineering. Another approach is suspended animation or cryogenic preservation. Instead of living through the journey, you sleep through it. This eliminates the sociological problems of generation ships, but introduces its own biological challenges. Currently, we cannot freeze and revive human beings. The formation of ice crystals during freezing destroys cellular structures. Some research has made progress with vitrification, a process that solidifies tissue in a glass-like state without ice crystal formation. But this has only been achieved for small tissue samples, not entire organisms. Some animals do hibernate naturally, and NASA funded research between 2014 and 2018 through a company called SpaceWorks Enterprises exploring therapeutic torpor for Mars missions. This involved inducing a state of reduced metabolism in humans for periods of weeks, not centuries. For interstellar travel, you would need suspension lasting decades or centuries, which is far beyond anything currently achievable or even clearly feasible in principle. A more radical solution involves abandoning biological bodies entirely. If consciousness is a product of information processing, then in principle, a human mind could be replicated in a computer. A digital consciousness could be transmitted as data at the speed of light, or housed in a very small, lightweight computer that is much easier to accelerate than a biological body. But this approach raises profound philosophical questions. Is a digital copy of your mind actually you? If the original biological you still exists, the copy is clearly a different entity with the same memories. And if the biological you is destroyed in the process, is continuity of consciousness maintained? These are not just philosophical puzzles. They are fundamental questions about the nature of identity and consciousness that would need to be resolved before anyone would accept digital uploading as travel. There is also the concept of von Neumann probes, named after mathematician John von Neumann, who formalized the theory of self-replicating machines. A von Neumann probe is a spacecraft that arrives at a star system, mines local resources, builds copies of itself, and sends those copies to further star systems. Each copy does the same thing upon arrival. The result is exponential exploration. Even at relatively slow speeds, say 10% light speed, such probes could theoretically colonize the entire Milky Way galaxy in a few million years through pure exponential growth. This connects to the Fermi paradox. If self-replicating probes are possible, and if any civilization anywhere in our galaxy ever built them, the galaxy should be full of them by now. The galaxy is over 13 billion years old. A few million years is nothing compared to that. So where are they? This question, first posed by physicist Enrico Fermi in 1950, remains one of the great unsolved problems in astrobiology. One possible answer to the Fermi paradox is that faster-than-light travel truly is impossible, and the sheer difficulty of even sub-light interstellar travel, combined with the vast distances between stars, means that most civilizations remain confined to their home systems. The speed of light is not just our prison, it may be everyone's prison. The universe may be full of intelligent life, but the light speed barrier ensures that none of it can easily interact. We are all isolated in our own little bubbles of reachable space, separated by gulfs of time that even the most advanced technology cannot meaningfully bridge. Now let me address one of the most counterintuitive aspects of time dilation as it relates to interstellar travel, because it offers a strange kind of hope. While 99% light speed is not fast enough from the perspective of people left behind, for the traveler, time dilation changes the picture dramatically. Consider a scenario where you accelerate at 1g continuously. 1g is the acceleration due to gravity on Earth's surface, 9.8 meters per second squared. This means you would experience normal weight inside your ship. You are not crushed by excessive acceleration. You live comfortably. If you accelerate at 1g for 1 year of your own subjective time, you reach about 77% the speed of light. After 2 years of subjective time, you are at 97%. After 3 years, 99.5%. The time dilation factor continues to grow. After 5 years of subjective time at 1g acceleration, you are so close to light speed that the time dilation factor is enormous. With continuous 1g acceleration for the first half of your journey and 1g deceleration for the second half, here is what the traveler experiences versus what Earth observers experience. To reach Alpha Centauri at 4 light-years, traveler experiences about 3.6 years. Earth time, about 6 years. To reach the center of the Milky Way at 26,000 light-years, traveler experiences about 20 years. Earth time, about 26,000 years. To reach the Andromeda Galaxy at 2.5 million light-years, traveler experiences about 28 years. Earth time, about 2.5 million years. To cross the entire observable universe, traveler experiences about 45 years. Earth time, about billions of years. This is astounding. With continuous 1g acceleration, a single human lifetime is theoretically sufficient to cross the entire observable universe from the traveler's perspective. You would arrive young enough to explore. But the universe you left behind would be billions of years older. Everyone and everything you knew would be dust, their civilizations risen and fallen countless times over. This creates a strange situation. The speed of light is not really a limit on how far a single person can travel in their lifetime. Time dilation means that with sufficient acceleration maintained for sufficient time, you can reach anywhere in the observable universe before you die. The real limit is on communication and connection. You can go anywhere, but you can never come home. Not to the home you left. But even this theoretical possibility requires continuous 1g acceleration for years, which brings us back to the energy problem. Sustaining 1g acceleration for years requires an unimaginable amount of energy. Using the best possible fuel, matter-antimatter annihilation, a 100,000 kilogram ship maintaining 1g acceleration for 20 years of ship time would require fuel mass many millions of times the ship's mass. The numbers rapidly become physically meaningless. So let us bring all of this together and look at where we actually stand as a species in terms of interstellar travel capability. The fastest human-made object as of the time of this research is NASA's Parker Solar Probe, which reached speeds of approximately 635,000 kilometers per hour, or about 176 kilometers per second. That is impressively fast by human standards. It is approximately 0.06% the speed of light. At that speed, reaching Alpha Centauri would take about 7,200 years. Breakthrough Starshot aims to reach 20% light speed, which would reach Alpha Centauri in about 20 years. But this is for a gram-scale chip, not a human spacecraft. And the required laser array of 100 gigawatts does not yet exist. Philip Lubin, a physicist at the University of California, Santa Barbara, has done extensive work on directed energy propulsion systems under a program called DEEPIN. His research explores how laser propulsion could be scaled from the tiny Starship probes of Breakthrough Starshot to progressively larger spacecraft. But the scaling laws are harsh. Accelerating a chip to 20% light speed is vastly easier than accelerating a human carrying craft to the same speed. The laser power and array size required scale with the mass being pushed, and a human spacecraft is millions of times heavier than a starship. Fusion propulsion offers another path. The British Interplanetary Society conducted a study called Project Daedalus between 1973 and 1978 that designed a fusion-powered starship capable of reaching about 12% the speed of light. The ship was enormous, over 54,000 tons at launch, most of it fuel in the form of deuterium and helium-3 pellets. It would reach Barnard's star, about 6 light-years away, in approximately 50 years. This was a one-way flyby mission with no ability to decelerate and enter orbit. A follow-up study called Project Icarus, initiated in 2009, has been working to update and improve the Daedalus design, potentially including deceleration capability. Fusion propulsion cannot approach 99% light speed. The exhaust velocities achievable with fusion are limited to a few percent of light speed at best, which limits the final spacecraft velocity through the rocket equation. But fusion could potentially allow us to reach neighboring star systems within a human lifetime, which is not nothing. It is merely not enough for exploring the broader cosmos. There is also ongoing research into antimatter propulsion. Organizations like Positron Dynamics, a startup company, have been working on more efficient methods of producing and storing antimatter. CERN has made progress in creating and trapping antihydrogen atoms for increasing durations. But we remain many orders of magnitude away from producing antimatter in quantities useful for propulsion. Current production rates would need to increase by a factor of roughly 10 to the 18 before antimatter propulsion becomes practical. So where does this leave us? Let me summarize the situation as clearly and honestly as I can. The speed of light is the absolute maximum speed for anything with mass, enforced not by engineering limitations, but by the fundamental structure of space-time itself. This is confirmed by over a century of experiments, from time dilation measurements to particle accelerators to GPS satellites. It is embedded in every successful theory of physics we have. Breaking it would require overturning the foundations of modern physics. Even if we could reach 99% the speed of light, the distances in the universe are so enormous that this speed allows exploration of only our immediate stellar neighborhood. The hundreds of billions of stars in our galaxy, the trillions of galaxies in the observable universe, the vast cosmic web of structure, all of this remains effectively unreachable at any sublight speed. The accelerating expansion of the universe makes this worse. The reachable universe is shrinking. Every day, more galaxies cross beyond our cosmological event horizon and become permanently inaccessible. We are losing the universe in real time. The engineering challenges of even approaching light speed are beyond anything our current or foreseeable technology can address. The energy requirements alone dwarf the total energy output of human civilization. The radiation environment, the interstellar medium bombardment, the fuel mass requirements, the deceleration problem, each of these is independently devastating, and together they form an apparently impenetrable barrier. General relativity permits theoretical constructs like warp drives and wormholes that could circumvent the light-speed barrier, but these require exotic matter with negative energy density that we cannot produce and may not exist in usable quantities. The Casimir effect shows that negative energy density is physically possible, but only at scales far too small for practical use. Quantum mechanics offers no obvious path to faster-than-light travel. Entanglement does not transmit information. Tunneling does not transmit signals faster than light. Tachyons almost certainly do not exist. The no-communication theorem appears to be absolute. But, and this is a crucial but, our physics is incomplete. We know this. General relativity and quantum mechanics, our two most fundamental theories, are incompatible with each other. They give different predictions in extreme situations, such as the centers of black holes or the first moments of the Big Bang. They cannot both be right in their current forms. A theory of quantum gravity that unifies them would be a revolution comparable to Einstein's revolution in 1905. And we have no idea what such a theory might imply for the speed of light barrier. We know only about 5% of the universe's content. Ordinary matter, the stuff that makes up stars, planets, and our bodies, constitutes about 5% of the total energy density of the universe. Dark matter makes up about 27%, and dark energy makes up about 68%. We do not know what dark matter is. We do not know what dark energy is. We have detected them through their gravitational effects, but their fundamental nature remains mysterious. Any breakthrough in understanding these components could revolutionize our understanding of physics in unpredictable ways. The history of physics teaches us humility. In 1800, people thought they understood essentially all of physics. In 1900, Lord Kelvin famously said there was nothing new to discover in physics, just more precise measurement needed. Within 5 years, Einstein published Special Relativity. Within 30 years, quantum mechanics had overturned everything. Concepts that would have seemed like pure magic to physicists in 1800, like nuclear energy, transistors, lasers, and GPS satellites, became routine technology within a century. We are now 120 years past Einstein's 1905 revolution. Who knows what the next 120 years will bring? The Alcubierre warp drive, even if impractical in its current form, demonstrates that general relativity permits faster than light travel in principle. The ER equals EPR conjecture hints at deep connections between quantum entanglement and spacetime geometry that we do not yet understand. Quantum gravity theories like loop quantum gravity and string theory suggest that spacetime itself might have a discrete structure at the Planck scale, and the implications of this for the light speed limit are unknown. None of this is a guarantee. It is entirely possible that the speed of light barrier is truly absolute, that no technology and no physics will ever allow it to be circumvented, and that intelligent life throughout the universe is permanently confined to tiny islands of reachable space. This is a real possibility that we must take seriously. But it is also possible that our current understanding of physics is as incomplete relative to the final theory as Newtonian mechanics was relative to relativity. There may be aspects of reality we cannot currently imagine, just as Newton could not have imagined space-time curvature. And in those unknown aspects, there might be possibilities for faster-than-light travel that we cannot currently conceive. The universe gave us brains curious enough to dream of the stars. It gave us the intelligence to understand that the stars are suns like our own, orbited by worlds like our own, possibly harboring life like our own. And then it placed a speed limit between us and all of it. This tension between our ambition and our limitation is not a cruel joke. It is the engine of all scientific progress. Every barrier that seemed absolute was a challenge that drove discovery. Heavier than air flight was impossible until it was not. Breaking the sound barrier was impossible until it was not. Splitting the atom was impossible until it was not. The speed of light is a fundamentally different kind of barrier. It is not an engineering challenge. It is a property of spacetime itself. Breaking it, if it is possible at all, would require not just better technology, but entirely new physics. But entirely new physics is exactly what every generation of scientists has discovered. And there is no reason to think that process has stopped. Now, I want to take you through one more critical concept that ties this whole discussion together, because it reveals something beautiful about the nature of the speed of light limit that most people never consider. Think about what would happen if there were no speed limit, if speeds could be infinite, if you could cross any distance in zero time. What would that mean for the structure of reality? It would mean that causality, the principle that causes precede their effects, would be destroyed. If you can send a signal at infinite speed, you can set up situations where effects happen before their causes. The future could influence the past. Logical paradoxes would become physical realities. The speed of light is not just a barrier, it is a protector. It protects the causal structure of the universe. It ensures that the past is the past and the future is the future. It maintains the logical coherence of reality itself. Without it, the universe as we know it, with its orderly progression of cause and effect, could not exist. This is a deep insight. The speed of light is not an arbitrary limitation. It is a structural necessity. It is the price of living in a universe where things make sense, where causes lead to effects, where time moves forward, where logic applies. Perhaps then, any method of faster-than-light travel that is actually possible would have to respect causality in some way. Warp drives and wormholes, if they work, might operate under constraints that prevent causal paradoxes. There might be versions of faster-than-light travel that do not allow you to arrive before you left. The universe might permit shortcuts through space without permitting shortcuts through causality. Some physicists have explored this idea. In the context of wormholes, Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel paradoxes. If you tried to use a wormhole as a time machine, quantum effects would destroy the wormhole before the paradox could occur. If this conjecture is correct, wormholes might be usable for faster-than-light spatial travel without allowing time travel, because the universe would automatically prevent any configuration that creates a causal paradox. This remains speculative, and the chronology protection conjecture has not been proven from more fundamental principles. But it offers an intriguing possibility. Maybe the ultimate barrier is not the speed of light per se, but the preservation of causality. And maybe there are ways to travel faster than light that do not violate causality, even though they violate the literal speed limit. Let me now discuss something that gives the problem an additional layer of depth. We have been talking about the observable universe, but there is good reason to believe that the actual universe is much, much larger than what we can observe. The observable universe is limited by the age of the cosmos. Light from objects more than about 46.5 billion light-years away has not had time to reach us since the Big Bang. But there is no physical reason why the universe should end at our observational horizon. Depending on the geometry of the universe, which appears to be flat or very nearly flat, based on measurements of the cosmic microwave background, the universe might be infinite in extent, actually infinite, or it might be finite but much, much larger than the observable portion. Some estimates based on the curvature measurements from the Planck satellite suggest the full universe could be at least 250 times larger in diameter than the observable universe. And it could be much larger than that, or truly infinite. If the universe is infinite, then even traveling at any finite speed for any finite time only ever gets you to an infinitesimal fraction of what exists. The concept of exploring the universe becomes meaningless for any finite speed traveler in an infinite universe. You could travel for billions of years at the speed of light and still have covered 0% of the universe. Not almost zero. Actually zero. Because any finite number divided by infinity is zero. This is humbling in the extreme. The universe may not just be too big for 99% light speed. It may be too big for any speed. It may be too big for the concept of travel to have any meaning on cosmic scales. We may be forced to accept that the vast majority of reality, if the universe is infinite, is permanently beyond our experience regardless of what physics allows. But let us come back from that vertiginous edge and return to practical implications. What should we take away from all of this? What are the action items for a species that finds itself conscious, curious, and confined? First, we should recognize that interstellar travel, even at modest fractions of light speed, is not impossible in principle. Reaching nearby stars within a human lifetime is physically possible if we can develop propulsion systems significantly beyond our current capability. Fusion propulsion, laser sails, or even far future antimatter drives could potentially achieve 10 to 20% the speed of light. This opens up the nearest few dozen star systems to exploration. That is hundreds of potentially interesting worlds, possibly including some with life. Second, we should invest in the long-term theoretical research that might someday lead to a deeper understanding of space-time. The physics of quantum gravity, the nature of dark energy, the deep connections between quantum mechanics and general relativity. These are not just abstract intellectual exercises. They are the research programs most likely to reveal whether faster-than-light travel is truly impossible or merely beyond our current understanding. Third, we should develop the technological capabilities that are achievable: better propulsion systems, closed ecological life support, artificial intelligence capable of managing long missions autonomously, and the ability to construct large structures in space. Even if faster-than-light travel remains forever impossible, these capabilities would allow us to expand within our local stellar neighborhood over timescales of centuries to millennia. Fourth, and perhaps most profoundly, we should make peace with the possibility that the speed of light barrier is real and permanent. Not in a defeatist way, but in the sense of adapting our expectations and plans to match reality. If interstellar travel can only happen at fractions of light speed, then perhaps the expansion of intelligent life through the galaxy will take millions of years. That is fine. 1,000,000 years is a blink compared to the age of the universe. If we survive as a species, we have time. The urgency is not about speed of expansion, it is about survival. A species confined to a single star system is vulnerable to extinction from natural disasters like supernovae, gamma-ray bursts, or asteroid impacts. Spreading to even a few nearby star systems provides insurance against extinction, and once established in multiple systems, a civilization can expand gradually. Building generation ships or slow automated probes, eventually spreading across the galaxy over millions of years. This is perhaps the realistic future of intelligent life in the universe. Not the dramatic faster-than-light galaxy hopping of science fiction, but a slow, patient, generational expansion from star to star. A crawl rather than a sprint. But a crawl that, given enough time, can cover an entire galaxy. There is something beautiful in this image. Not the dramatic beauty of a warp drive or a hyperspace jump, but the quieter beauty of persistence. Of a species that looked at the speed of light barrier, understood it, accepted it, and chose to expand anyway. Slowly, patiently, star by star, generation by generation, building a civilization that spans not just worlds but light years, connected not by instantaneous communication, but by the patient exchange of signals across years and decades of travel time. This is not the future most people imagine when they think about space travel. It is slower, quieter, less dramatic, but it is the future that the laws of physics actually permit. And it might be enough. Enough to explore millions of worlds. Enough to find other life. Enough to ensure that consciousness, having emerged in this universe, persists and spreads for billions of years to come. Let me now bring this discussion to something I find particularly fascinating, which is the relationship between information and the speed of light. Because ultimately, the speed of light limit is really an information limit. And understanding it as an information limit reveals something profound about the nature of reality. In 1948, mathematician Claude Shannon published his foundational paper on information theory. Shannon showed that all communication, all information transfer, can be quantified and analyzed mathematically. His work laid the foundation for the digital age. But Shannon's information theory, combined with Einstein's relativity, reveals a deep constraint on reality. Every physical process can be understood as information processing. Every interaction between particles, every measurement, every observation involves the transfer of information. And all information transfer is limited by the speed of light. This means that no physical process, no matter how exotic, can ever produce effects that propagate faster than light. Not because of some specific mechanism that prevents it, but because faster than light information transfer is a contradiction in terms within the framework of relativistic physics.